Okay, so yeah, thank you for joining us. So the hackathon has 4 different groups, and you're speaking to the PDE group today. If we have people from Caltech, Berkeley, Los Alamos, Michigan, and ETH. And many people know you, but not all. So yeah, just do a quick intro to your setup, and then yeah, let's jump right into the talk. Thank you again for joining us.
Sure, great. Let me share my screen. Okay, can you all see my screen?
Yes.
Okay, perfect. Okay, so yeah, so I'm sorry I'm not there in person, and I'm actually very unhappy about it. It's of course all on me because I was fortunate to attend the workshop on the scientific foundation models that Karthik organized a couple of months ago. It was fantastic, and I learned a lot, even though I was there only for one day. But we have a whole summer school going on here, so unfortunately I can't make it there. So I'm very excited to tell you about some of the work that's going on in the climate community and using AI and building emulators and foundation models. And I believe that you have already heard from other people. I think Paris was there, maybe Anima, about some of these. So I'm going to tell you a bit about our perspective and what we are working on and the areas that I think would be great for collaboration between different disciplines. So to tell you about myself, so my training is actually in fluid dynamics and computational physics and to some degree applied math. And then I did a postdoc in a climate science department, and I started doing more work on extreme events and climate change. And then over years, I did more stuff with data-driven methods from statistical physics. Then I got into deep learning, and now like my group mainly does work at the intersection of climate science and deep learning. So at the beginning of this talk, I'm going to talk a little bit about climate research, just to really tell you about some of the challenges and open questions that we have. And I think that would help with better explaining why we are basically excited about using AI in a specific ways and some of the advances and some of the challenges. Now, it's sometimes hard in a remote talk to interact with the audience, but I don't have a lot of slides. I have around 30 slides. And it would be great if you just, engage. And if you have questions, comments, please just unmute yourself and ask your question or make your comments. That would be much more fun. And I know that there is time for discussion after that. Okay, great. Okay, so as you know, climate research is increasingly becoming more important and more popular. This is basically a very multidisciplinary field. It involves basically first understanding how the Earth system would respond to changes in external forcings, like changes in greenhouse gases, how the global temperature would change. But more importantly, we need to understand how extreme events, heat waves, hurricanes, droughts, atmospheric rivers would change at different regions because of these basically global changes. Then we need to quantify the socioeconomic and environmental impacts of these changes, and then formulate mitigation and adaptation and even climate engineering solutions. Now, as you can imagine, the challenge here is that we really need to quantify the complex interactions among a number of highly complex systems involving the Earth system and the human society. And over the past few decades, in different disciplines, people have developed all sorts of tools to basically work on each of these steps. And the problem is that these tools are imperfect and they all come with some degree of uncertainty. And the main problem is that at the end, when we put everything together, we end up with very high uncertainties about, for example, how hurricanes would change in New York City, in Texas, how heat waves over California would change, and things like that, which, as you can imagine, make adaptation and mitigation strategies extremely difficult. And it's very common to see these kind of headlines in the news about problems with these very expensive and controversial mitigation adaptation strategies. So the main tools that we have to use in climate science, especially when we ask questions about the future, whether it's just forecasting of weather or longer term climate projections, are climate models, which are basically computer models. Now, the state of the art is actually a result of a slow revolution that took over 50 years. This is how we figured out how to numerically solve the governing equations for conservation of mass, momentum, energy over for the Earth system by basically doing computational fluid dynamics. So it's like Navier-Stokes equation is basically the fundamental equation in all these models, and then there are a lot of other kind of physical components we add to them. Just to tell you a little about the history of this, so this field actually started by John von Neumann using the first digital computer, ENIAC, as his first civilian application to do weather forecasting. And then people who were working for him, including Suki Manabe, who a couple of years ago received the Nobel Prize in Physics, they took that, developed climate models, and now we have all these climate models that can produce the kind of simulations that you see up there. And as many of you know, actually this whole field started a bit earlier when Richardson did the first forecasting by solving the equations, which actually didn't quite work out. They did it once and then they gave up because it blew up and produced very unphysical results. Around 20 years later, Courant and others figured out what was the problem with this forecast, which was the CFL condition. And still it took another 20 years for von Neumann to do the work that he did. And in between, I should say that actually climate science always had a part that involved doing data science. And it was a school of basically metrology that was led by Erwin Craig at Caltech, who was basically doing analog forecasting. He was trying to match weather patterns to do forecasting. And then on the other side, there were people like Rossby, who was actually the chair of the metrology department at U Chicago, my current department. And they wanted to solve the PDEs. They wanted to solve the Navier-Stokes equation, except that they couldn't do it. And in fact, there was a lot of tension between these two sides. But after von Neumann's work, basically people really started doing more and more in the direction of looking at the first principles, solving the equations. And after like 50s, people were still interested in this kind of data-driven weather forecasting. Ed Lorenz actually was interested in this, but he wrote a paper about this kind of finding analogs. And he argued that it's actually would be very difficult to find analogs for weather patterns. That he was, of course, very interested in chaos and the fact that even if you have a small differences between two analogs, the like 10-day forecast would end up being very different. And so after this paper, people basically stopped really caring too much about this kind of data-driven forecasting. There's another paper that took this idea and even put a number on it. And you can see it in the abstract that they argue that you need 10 to 30 years of data if you want to do weather forecasting just with data. But as you all know, and I'll talk about it more, it turned out that actually that's not true. And even like 40 years of data would enable us to do better than any of these physics-based models. Okay, so as I mentioned, there has been a lot of progress in climate modeling and weather forecasting based on physics-based models. The problem is that as we try to make the physics-based models better and better, they become more complicated and more expensive. Again, a very similar problem that we have in fluid dynamics, turbulence modeling. We have to go to higher and higher resolutions. And of course, the problem is that the climate system is a very, very multi-physics and multi-scale system. The cartoon here is just a simple reminder of the length scales and the time scales that we have in the atmosphere alone. And because everything is non-linearly interacting, we can't really just focus on one scale. This cartoon here on this side is basically just a representation of how the resolution of climate models basically has evolved over years. This is the Moore's law. These are the resolution of the current models. You see that sort of like currently we are at 100 kilometers. And even the models haven't really improved, that they couldn't have followed the Moore's law, and there are a few reasons for that. And so as a result of this, you see that we are very far from getting to this resolution of 1 kilometer that people generally believe that would be a resolution, at least in the atmosphere, that can give us very accurate simulations, that we can basically turn off most of the closure models, most of the parameterization. So you see that we are very far from getting close to this, what people call the digital twins. And as you know, the scaling here is actually cubic. So to go from the current resolution of 100 kilometers to the 1 kilometer resolution, it's like 1,000,000 times more expensive. The improvement in weather forecasting has also been pretty slow. These are just some plots from this paper that basically term this a major achievement in basically in science, in computing, in climate physics, but still it happened over decades. And basically referring to this as a revolution comes from the title of this paper. Okay, so before getting into AI, just a couple of more slides about really what the big questions are and the big challenges are in climate and weather forecasting. So when we try to do weather forecasting or climate change projections, there are three kind of uncertainties that we are dealing with. So one is the epistemic uncertainty. This is basically the structural error, the climate model error, like your equations are imperfect. Mainly in this case, the parameterizations are imperfect. We also have internal variability uncertainty, the fact that we are dealing with a naturally evolving chaotic system. So if you don't have enough data, you have a small signal to noise ratio. And then the other one is the scenario uncertainty, that we don't know how much CO2 we are going to put into the atmosphere or remove. Now, I think these are the three common uncertainties in many problems in science and engineering. Like in engineering, scenario uncertainty could be different design choices that you can make, different boundary conditions, different forcings. Internal variability is always there when we are dealing with like chaotic systems, turbulent flows, and epistemic uncertainty is, of course, something that we have in many models of physical systems. Now, in climate system, there has been a lot of work on trying to quantify the contribution of these uncertainties. And now we have plots like this that basically shows you that, for example, if you are trying to predict the global temperature, mean temperature in 2040, what percentage of the uncertainty comes from each of these sources? So for example, in 2040, 50% of the uncertainty would come from model error, basically just bad closure models. 40% of it would come from the scenario, and 10% is internal variability. Now, looking at this, you might think that, well, internal variability is the smallest one and we shouldn't care about it. But it turns out that actually when you go to like smaller scales and then variables that are more related to dynamics like precipitation, wind, then internal variability can actually become very important too. So here, when we go to a smaller region, you see that, for example, in 2040, model error is still around 50%, 10% is the scenario, and then 40% is internal variability. And in fact, as you look more and more at extreme events, which are rare, all these three sources become very important. Now, you might not have seen these kind of plots before, but probably you have seen these kind of plots that people show, for example, global surface temperature over years. We have pretty, we have confidence in the period we have observed, but after that, there are different lines. Those are because of different scenarios. And the shading is a combination of the model error and internal variability. Now, the challenge is, like many other problems in science and engineering, to improve the models, to reduce the epistemic uncertainty, we often have to go to higher resolution models, which become more expensive. But to explore different scenarios or to get a better signal to noise ratio, we have to do more ensembles and longer simulations. So these are basically, we need faster models and more accurate models, and it's hard to have them together. Basically, people either try to come up with reduced order models so that they're fast, but often use accuracy, or you go to more and more complicated, more expensive climate models, but then it would become very difficult to explore different scenarios and reduce internal variability. So now the question that people have started asking from around 2017 has been, well, can AI help with reducing these uncertainties? So next, I'm going to tell you about some of the ideas and then more focus on the ideas about emulators and foundation models. But before I go there, is there any question?
I think you've been very clear and very, the motivation's also very good. So, so this kind of breakdown, of course, it's approximate, right? But what is happening in the physics world other than resolution, right, to address the epistemic?
Yeah. So that's a great point. And of course, we hope that by doing more research on the fundamental physics, developing better parameterizations, some of these improvements should come from just having a better understanding of the system. Now, it turned out that actually, to a good degree, the improvements come from increasing the resolution. Like, actually, I don't have the abstract of this paper, but if you look at it, they actually pointed out that, at least for the weather forecasting, the improvement mainly comes from the improvement in the resolution and one very important point of data assimilation. So if you look at this plot, actually, there is no major jump anywhere, except something around like late 90s. You can see that the difference between southern hemisphere, which is this lower line, and the northern hemisphere forecasted scale closes, and that's where they move to four-dimensional variational data assimilation. So at least in better forecasting, most of the improvement come from better data assimilation and high resolution models. In climate, of course, I think we have better parameterizations for each process, but the problem is when you put all of these parameterizations together, it's still the interactions. Sometimes actually you start canceling some of the, like before you had some results that look good because of error cancellation. Now you have better parameterizations for some processes. That goes away, you actually get worse results. So there has been a lot of work on developing better parameterizations, better knowledge of the system, but it has become hard to translate that into actually reducing the uncertainty from model errors.
Yeah, I think that's good insight for someone like me who's outside, right? So most of those things are kind of tapering off, and what's left is resolution and algorithms. Yeah.
Exactly. Yes.
Yeah.
Any other questions?
Nothing in the room, at least. Yeah, keep going.
Okay, great. Okay, so of course the question has been how AI can help, and around 2017, 18, a lot of people started working on using AI, and there the idea was AI can be most helpful in actually developing better models, reducing the epistemic uncertainty, sort of what Kartik alluded to, maybe use AI to develop better parameterizations or even accelerate the theoretical understanding. And still, I would say this is the a biggest percentage of the climate community is still working pursuing this direction. And there are ideas about how to combine all sorts of regional and global simulations, satellite data, theory, and AI to improve the understanding, develop better parameterizations. But a direction that was sort of surprising and unexpected, and that in the past year and a half has really basically exploded in terms of popularity, and I explained why, is this idea that, well, maybe we can build these fast AI climate emulators that can be used to actually reduce this scenario uncertainty and internal variability uncertainty. So I went through this whole, couple of slides about the uncertainties to just clarify that all these three uncertainties are important, and reducing them, any of them, can actually be very valuable. Now, I'm not going to talk about this direction of AI for better parameterization or physics, but we have a review paper that's written for a broad physics audience, and it's on arXiv if you're interested. We try to talk about some of the advances and challenges in this direction. But mainly, I'm going to talk about this direction of AI climate emulators, or now what we call them climate foundation models. And this, basically, the popularity of this direction is really a result of this incredible success of weather forecasting just from data. The idea that I mentioned people were interested in before digital computers became available, then they thought that we don't have enough data to do anything like this, and now it turned out that actually works pretty well. So the idea here, and I think Paris gave a talk and probably talk about Aurora, which is like the kind of model that I'm going to talk about. So here the idea is, let's just not think about Navier-Stokes, about first principles, about any equation. Let's just take a big neural net, D, with parameters we want to learn, theta, and we take the global state of the atmosphere, like this vector U is the state vector. It has velocity, temperature, different levels, basically all over the world, relative humidity, surface pressure. You all put them as one big vector at the current time, and you try to predict it like a few hours or even up to a day later. And to march in time, basically, you put this back and auto-regressively, you integrate for as long as you want. And to find data, of course, you can think of using a simple MSC logs. And many people have started, like not many, but some groups, including my group, started playing with this idea in 2018, 19. And most people thought that they don't have really enough data to do this, at least based on the observational data that's available. And surprisingly, at some point, we found that actually this can be pretty promising. So one of the first papers, and maybe the first paper that showed this, is this paper that introduced this model called ForecastNet. The development of this was led by NVIDIA, by Anima, whom you know, and Kartik Kashinath, and my group and a couple of other groups contributed to this. So this is a model that uses transformer with FNO used to accelerate the transformer. And we found that actually this model can have accuracy comparable to the best numerical weather model, which is the model from the European Center. This actually is already better than the US system. This model is trained on only 33 variables from 40 years of data that we have. This data is called reanalysis. It's when you put observations and do data assimilation, and then you can get gridded data. So this is pretty close to the truth. The key is that this model is around 100,000 times faster and cheaper, like less computing, requires less computational cost than the numerical model. This is just an example of the performance of this model. Here I'm showing you water vapor. This is global water vapor from the truth, from ERA 5. And this is the out-of-sample forecast of this model, which as you see, it's actually pretty good. Like if you're interested in atmospheric rivers, like making landfall over California, even like 4 days, 4-day lead time is actually doing a pretty good job. If you look very carefully, there are some like smaller structures over the tropic are missing, and I'm going to talk about that. But overall, this is actually pretty remarkable. And soon after this, a lot of big tech companies started developing weather models, mainly by going to bigger models and doing more ML engineering. And very soon, these other models emerged. The one is called Pangu from Huawei, the Chinese tech company, and GraphCast from DeepMind. And Pangu is transformer, GraphCast is a graph neural net. And these models showed that you can actually now very robustly beat the best numerical weather models that we have for up to like 10-day weather forecasting. These are just some examples of the performance of Pangu. Here, the black line, this is the track of the typhoon. This is another one. So that's the ground truth. The blue line, this is the best numerical model. This is the high resolution European model. And you see that it's fine at the beginning and then it diverges. And the red, that's the Pangu model, which you see that it actually works pretty well for a few days. And then, of course, a lot of people are still very skeptical until the people at the European Center took these models and really thoroughly examined them. They validated them against all the metrics that we currently use to validate the numerical models, and they found that these models are actually pretty good. They have some problems, and I'll mention some of them. But again, in terms of the common accuracies that you are interested in, like, for example, figuring out whether it's what is the temperature in Ann Arbor in 5 hours or tomorrow, these models actually are better than the physics-based models. And now the European Center has developed its own AI model. It's called AIFS. And here you see that, for example, 60% is usually the pattern correlation that consider like the limit of accuracy. You see that for like around 9-day forecast, you gain half a day from the AI model. But again, the key here is this major reduction in the computational cost, which enable us to do probabilistic forecast and to do a lot of other things. Before I move forward, is there any question so far?
No, this is very good. So I think one of the things we really want to zoom in on, maybe during the presentation or maybe in the discussion is, yeah, what are those problems for which, what are the problems, right, to be improved upon? And also, the last couple of weeks, we've been pretty much zooming around this question of what are sweet spot problems for AI for science? And this is absolutely one of them, right? Because it's very rare in many disciplines of computational science involving PDEs, especially where the physics model is not good, and then the AI model comes and improves upon it, right? That's almost never the case. So in that sense, this is a beautiful problem. but we also want to like figure out where it doesn't work well and what are these other things. So yeah, whichever way, I mean, you may already have that content in the slides, but if not, we can discuss after your talk.
Yeah, absolutely. I mean, both of the points you made, I think those are exactly the ones that I mean we are interested in, and I think it would be great to talk about them. So I will mention some of the problems that these models have, and then we can also so it would be great to chat about them during the discussion. But also to the other point, I really believe that this is one of the biggest achievements of scientific ML so far. Because so I have this up here. So the first deep learning for climate workshop was in 2019 in Oxford. And basically the consensus was that we are 10 years away from getting close to this European model accuracy, which is the gold standard of accuracy, weather forecasting. We are 10 years away from being able to use AI to do this kind of forecasting. And there were people there who have been visionary in the work they had done before in bringing novel tools into climate science. And even those people were all like, this is not going to work anytime soon. And just 3 years later, ForecastNet did this, got basically comparable accuracy than IFS. And just a year later, IFS did that. This Pangu and GraphCast actually beat the European model. And again, it's also not something that you just read in a paper. It's actually something that everybody now agrees on. People in the European Center, in other places, have really examined these models. And basically the metrics that we use to evaluate weather models, these models are actually good. They're actually useful. Like at this point, you can go to the European Center's website and get the forecast from the AI model. But of course, there are problems, and that's what I'm going to talk about next. So, but I wanted to go back to this and point out that actually this is the reason, like this success of the AI weather models, it was really changed, shifted the attention of many in climate science community from focusing on these parameterizations and reducing epistemic uncertainty to actually building these fast climate models, climate emulators, because you can reduce these two uncertainties, which are as important, even maybe in some cases more important. And so now you basically see about this a lot in the news. For example, this is from Nature, that basically now they talk about the fact that the speed up in climate modeling is where AI can actually be very useful. And maybe the improving the accuracy is something that we hope that can happen. Probably it's going to take longer. But that's where really the excitement comes from. The fact that you can just data-drivenly predict these kind of systems that we always believe is very, very complicated. So really, at this point, everybody agrees there is a second revolution in short-term weather forecasting, short and medium term, up to like 10 days. These models are now very good. So the next question is, can we actually get to longer time scales, like sub-seasonal to seasonal, something that's called S2S? Now, interestingly, at this kind of time scale, we have never had a revolution, because here you need to do probabilistic forecast. This is well beyond the Lyapunov exponent. So you are not going to get a trajectory, but you hope to get some sort of probabilistic forecast. You cannot really use the numerical models to do this. And there are simple statistical models that basically have a pretty poor accuracy. So actually, this is a great opportunity to have even like a first revolution. Now, S2S is very important for agriculture, for planning, for a lot of applications. So this is like one of the areas at UChicago we are focusing on, because, for example, in our econ department, there has been a project for a few years to improve S2S forecasting using traditional methods for farmers, especially in low-income countries. And they have shown that this can actually save hundreds of billions and even trillions of dollars over several years if you can do this. But again, like just relying on traditional models has basically been very difficult. So there's a lot of excitement in AI for this direction. Now, the first problems I want to mention is that, well, the current AI models actually become very unphysical after you run them for a few weeks. And this is something I'm going to talk about more. The other question is, well, we are just learning from data, right? So what happens to the rare events, and rare events, extreme events are actually the most impactful ones. So what happens to the kind of events that might happen tomorrow? They're very like physically expected, but we have never seen them in these 40 years of data that we have. And especially in the context of climate change, people have been talking about this in the climate community as gray swans, events that are not black swans. It's not like, something very, very surprising and unexpected. These are events that, like a very strong hurricane or very strong heat wave, that are expected, but we just haven't seen them in 40 years of data. So the first point about these models become unphysical. So these are just some examples of like kind of longer rollouts from some of these models. This is ForecastNet, Pangu with 1 hour time step, GraphCast. And you see that these models become very unphysical. What I'm showing you here is basically the shading is what's called Z500. This is a string function in the atmosphere. These are just, if you running this for a couple of more days, you just get infinity or none. And then there are now some models that they don't blow up, but they give you very unphysical results, and you see them here. But if you're not an atmospheric scientist, it may not be very clear that these are unphysical, but I can later show you some plots that these are basically all unphysical. When you get to 30 days or longer, the models become unphysical, which makes it hard to use them for this kind of S2S or even for any kind of climate application.
So Pedram, just a hypothesis or a thought here, right? So if you're looking at 2 weeks or things like that, and you have some kind of hurricane that is forming, and then you do the prediction and it's doing well. So and we have evidence that works well, right? But at the same time, can these methods, even over 2 weeks, from nothing, predict that this hurricane is going to form, right? And then it's going to move. So that's kind of emergent phenomena, right? So even within that 2 week time frame, can it like do things like that?
Yeah, that's a great point. So to some degree, they can form hurricanes on their own. But also formation of hurricanes, it basically requires the hard, like a warm sea surface temperature, which you might have in your initial condition. But also these kind of models currently do not account for the interaction of the hurricane with the ocean. And that's can be very important for the formation of some of the strong hurricanes, because these models don't have an active ocean. So you're basically imposing the sea surface temperature. Same problem with land, like soil moisture feedback can be very important. So as a result of these, actually a lot of people are now thinking about building coupled models, a model that basically is an emulator for atmosphere and ocean together, or atmosphere, ocean, land together. So I don't know if I answered your question, but yes, most results look at the accuracy for a hurricane that's already formed, and you get the track correctly. But the bigger question, I think that's what you are alluding to, is can you even get the initiation, like a formation of something that wasn't even in the initial condition?
Yeah, very, very useful. Maybe that's what would be very cool. Yeah, very cool insight. Thank you.
Okay, and I will come back to this instability problem. But before that, let me also tell you why we think that this can even be useful for climate change. Because of course, a model like a weather model that's trained on the current climate, there is no way they can tell us anything about, 50 years from now when we are going to have almost let's say twice CO2 in the atmosphere, right? That's a non-stationary system. So the model wouldn't work. But here is an idea that's emerging about how to use these models even for climate. So before, what I showed you was the idea of using these models as initial value solvers, right? So we didn't have this term that I'm going to tell you what it is. We just took an initial condition. We found the answer 6 hours later. We did other regressive integration. Now, let's say that we also start accounting for the boundary conditions, like, for example, the sea surface temperature, the land, the ice, even like the radiation from the sun, to get the seasonal cycle. So really, you can think of this as some sort of boundary value solver. So now I have an input that accounts for all these boundaries of the atmosphere. And so I'm going to evolve this atmosphere subject to these boundary conditions that I've imposed. Now, the nice thing is that the boundaries to the atmosphere actually move very slowly. For example, sea surface temperature evolves at the time scale of weekly or even monthly, while the weather evolves at the time scale of hourly, certainly daily. So we have these slowly moving boundary conditions that even we have good ideas about how they would evolve. So we can impose them as boundary conditions on these models. So the idea that's really emerging is this. So let's just train these emulators on a bunch of different climate simulations. So we can do high resolution simulations under different things, like you can choose different CO2s, different aerosols. And let's say we have like a bunch of 50-year simulations at resolution of 10 kilometers, because these are short rather than 100, maybe we can afford 10. And we are going to train these models on these kind of simulations. Now, if the model is stable and remains physically consistent, you can now do very cheap inference. And for example, for a given S, that this S is related to CO2 and things like that, now you can do a much, much, much longer integration and then look at the PDF and figure out that, for example, under 2 climate conditions, how the rare events would change. So using these AI emulators, climate emulators this way, we are not going to reduce the model error. We are not going to ever do better than the numerical simulation that we had, but we are going to be able to reduce the internal variability and the scenario uncertainty. Because one idea is that with this kind of model, you can interpolate at least between different scenarios. And if you talk to people in econ and in public policy, a lot of times they're asking the question of, well, you have simulations for 4 times CO2 and for 2 times CO2, but what happens if you have 3 times CO2? Can I calculate the cost benefit basically balance for that kind? And then the challenge is to go and spend millions of CPU hours to do another climate model simulation. But with this kind of emulator, the idea is that we can even interpolate between these. Now, of course, there is a huge if here. And that if is, if you run these models for, let's say, 500,000 years, the model would remain stable and physically consistent. It's not going to drift. And you can really trust the extreme events that you get from this model, which, as I already sort of told you, the models currently cannot do this. Okay, so before I move forward, is there any question about this?
I had some questions myself. This stuff is really interesting. I'm very happy that I'm, able to listen to the work that you're doing and your group is doing. I guess I'm still a little bit stuck on this boundary stuff. Like you talk about how, okay, we have a lot of this considerations we can do. We can also maybe in the future try and couple things together. But to what extent can you push these boundaries?
You mean by boundaries, you mean these boundary conditions,
Yeah.
or
Yeah.
to build coupled models?
I guess for the main first point.
Okay. Yeah. So, for example, there are things like solar radiation that we have a pretty good idea about. Like that's completely external. We know, the solar cycle and seasonal cycle, so we can impose that. Things like how the sea surface temperature, the land, the ice would change. We can get them to a good degree from lower resolution models, even from like energy balance models.
Mm-hmm.
The problem always has been to get things at the weather time scale and length scale, because for mitigation adaptation, like for example, I lived in Houston before, and the city of Houston doesn't really care about how the global average temperature would change. They care about how the heat waves of Houston would change, or how the hurricanes of Houston would change. And there is a lot of regional dependency, right? In some places, hurricanes are going
Right,
to...
exactly, yeah.
Yeah,
Mm-hmm.
so the challenge always has been to get things at the finest scales that are needed for policy making. I mean, the global change in the global temperature, like RNUs, like did a back of the envelope calculation, got it like pretty closely. So back to your point, so here really what we are doing is we use these emulators to interpolate between the boundary conditions on the weather time scale and length scale, which is the part that has always been very difficult.
Mm-hmm. So only interpolation though, because I guess you had a slide earlier about saying something along the lines of, yeah, how do we handle like a challenge that, needs to be considered is handling the extreme events, right?
Yeah, that's a great point. So we want interpolation between boundary conditions and like, let's say different CO2,
Right.
but you still need to be able to extrapolate at the, like for a stationary climate, still the rare events, if you want to get them, you need some degree of extrapolation, right?
Yes.
But that's the area where I will show you that these models cannot do. And like back to Kartik's question, I think that's an area that really we need AI in science. We need physicists, machine learning experts, numerical analysts, they all work together to enable these models because it's a data imbalance problem, right? So extreme events are rare, or maybe you even haven't seen them. So how would you enable the model to get there? But the point I'm trying to make here is that, I mean, a lot of people say, well, these kind of AI weather model, the success cannot be translated into addressing climate change. But here I'm saying that actually there is a way to do that. But of course, there are these other questions we need to address.
Thank you very much. Yeah, thank you for the question too. Yeah.
Okay, great. So back to this question. Well, can we actually run these models even for like 4 weeks, 5 weeks, and then you see these results that I showed before, the models become very inconsistent, very unphysical. Just to give you a better idea, here there are some of these models you can run to 10 years, they don't blow up. So here for those models, I'm showing you the average zonal wind at like 10 kilometers above the surface versus latitude. The black line is the truth, the error 5, and you see that none of these models actually get you the right circulation. And even some of them start doing some, weird stuff near the poles and things like that. So currently these models don't remain physical when you run them for longer times. So some of the work that we did earlier was about, well, can we understand where this problem comes from? So we started looking at the spectrum of the predictions. So here what I'm showing you is that for the wind at the 10 kilometer, basically above the surface at the 10-day prediction, this is basically the spectrum of the wind. This is basically done over, spherical harmonics over different wave numbers. The black line, that's the truth from era 5. And you see all these models, which some of them have pretty good forecast skill over 10 days, they get the larger scales correctly. Like this peak here, this is the weather scale. But then you see that at the smaller scales, they're all incorrect and they do some weird stuff. Even when we look at the one time step prediction, we see the same behavior. So at one time step, which is usually like 6 hours or 12 hours, all these models have pretty high accuracy, like 99.9% pattern correlation and pretty good spectrum up to wave number 3040. But again, you see the small scales are bad. Now, interestingly, the ones where the prediction goes above the true spectrum, those are the models that if you keep going, they would blow up. And the ones that are below are the models that don't blow up, but remain unphysical. Now, if I show this to a CFD person, probably they say, oh, you have one model that has this too diffusive, right? So it's a stable, but in physical, and one model that doesn't have enough, hyperdiffusion or something, and it's blowing up. Now, remember that here, there is no equation, right? We just learned from data, doing prediction with data, but we see this kind of behavior. So in our group, we have always been looking at the hierarchy of models to answer these kind of questions. We started applying these kind of analysis, building emulators, doing Fourier analysis on this hierarchy that goes from like Lorentz to Chromatosavichinski to turbulent flows, all the way to weather and climate data. So going back, again, these are the results I showed you before, like forecast net on 25-kilometer data. And you see, this is a spectrum just plotted in a different way. The red is the truth. These are the forecasts from the model. Even though you have good forecasts, like after one time step of 1 day, 0.99, you see that the spectrum is wrong. These spikes here, these are actually not the reason cause of the instability. They come from the transformer, and they have been fixed in the newer versions. So we thought that, okay, maybe 25 kilometers is just too small a scale to learn. Maybe forecast net, we have to look at the different architectures. So we just took a simple unit at 200-kilometer data, and we saw the same thing. Like after one time step of a day, high forecasted scale, but you lose the smaller scale. And here you clearly see that this error goes up, and then at some point, visually, you see the instability. We thought that, okay, maybe the weather is just too complicated. So we went to a simple turbulent flow. This is just basically 2D turbulence that mimics the atmospheric oceanic turbulence called quasi-strophic turbulence. We have the full state vector. We have very long data sets, and we saw the exact same behavior. So high pattern correlation after one time step of 5 hours, you look at the spectrum, we have missed the small scales. And some of you might recognize the problem, and this is basically a spectral bias that neural networks have this fundamental challenge in learning high wave numbers, high frequencies. And there are some nice papers in the ML community about where this comes from. In a very hand-wavy way, the neural networks drop the loss. They figured out it's better to first learn the larger scales, but by the time they learn the larger scales, the loss and its gradient are too small, so nothing gets updated and you sort of saturate. And it's basically everywhere. It's not, go ahead.
this is this classic, when I first saw the success and weather prediction, at least my intuitive understanding was, these things can predict as long as the small scales aren't coming back to kill you, right? So that's pretty much precisely what you're saying.
Like the universality and no backscatter.
Yeah, exactly.
Universality hold, but no backscatter, like.
Correct. I mean, this is almost the entire problem with almost any turbulent flow where.
Although in 2D turbulence, they have this backscatter problem, right? Which the large small scales are in the spectrum go back to the large scales, so.
Yeah.
Absolutely. So you guys are well ahead of me. Exactly. So these are the things that, like, for sometimes for other audience, I actually have to explain exactly. So these are the problems. So in 2D turbulence, we have inverse cascade, which is actually energy goes up. So small errors in the high wave numbers actually can go up. So here you actually see that evolution of the error, that you see that first time step, second time step, and then after a couple of days, visually you can see the problem. So the first problem we identified is that you lose accuracy from the beginning. Every one time step, you get these errors. I'm not going to go through the details of where spectral bias comes from. Probably most of you know about this, but there's been some nice work showing that it's a real optimization problem. Sometimes people look at this and say, well, it seems that, it's like an approximation error. You don't have, an expressive enough neural net, but you can go deeper and deeper and bigger in the neural net. This is not going to go away. So, and the point I will make later is that I think it's important to understand where these errors come from so that we can actually fix them for the right reason. But the second problem, as Karthik mentioned, is now the error would actually accumulate, right? So it goes up. So to solve this problem, the first thing we did, we actually added a spectral regularization to our loss function. So this is the original MSE loss. We added a term here that basically says, okay, I'm sort of losing the accuracy from wave number 20. So let's add a term that would make sure that the Fourier coefficients after some threshold wave number are basically captured well. Now, the problem is that this is a very easy solution, but it's not a perfect solution for a system that has continuous spectrum, because whatever wave number I pick, again, there would be a small wave number, large wave number. And when you expect to do millions of time step integrations, at some point, these small errors would come back and affect your solution. The other thing we did was that we actually started doing our integrations not by taking the current state, predicting the next one, but by doing things like Euler or even Runge-Kutta. Like Michael Mahoney actually has a nice paper about showing the importance of doing this so that you actually get convergent methods. So with the current weather models, and some of the papers have shown this, including a paper we have, if you decrease the time step, actually the accuracy decreases. So to do a 2-day forecast, it's better to do 2 one-day forecasts rather than 48 one-hour forecasts, which is the opposite of what you have in numerical methods. But if you do these kind of things, you get convergent simulation.
Sorry,
So anyway, go ahead.
Could you repeat that comment about this 48-hour to 1-day thing? I think you were a bit fast there.
Oh, do you want me to repeat it?
Yeah.
Oh, sure. Yeah, and sorry, yeah, I'm trying to go a little fast so that I get to all the slides. But again, I think it's more important that, we can discuss this. So basically, there have been a few papers that have shown for weather models, but even for simpler nonlinear ODEs, PDEs, that when you have algorithms that take the current state and predict the next one, if you decrease the time step, the accuracy of the forecast decreases, like when you do autoregressive forecasts. So basically, I mean, if you go back to numerical analysis, we have the local error, right? The truncation error, and then you have the error accumulation, and we have methods to analyze it, as you know better than me, to eventual prediction after, let's say, 10 time steps is more accurate when delta t goes to 0, right? The AI models, at least if you just take the current one, predict the next one, they don't have that because the way that the error accumulates.
Yeah. Got it. Yeah.
And it's not just AI models. Many other models, like again, Michael Mahoney has a paper that he showed it for very simple ODEs. So we put this Fourier loss regularization, Runge-Kutta integration together, and now we actually have a stable integration. So this is from that turbulent flow. So this is the jet, like 100,000 day of integration. These are the POD, EOF, the first two modes. So you see that the jet has the right variability. Even now, when we apply this to the reanalysis data, we actually get stable simulations. This is how what happens when you actually add this regularization, you see that you can capture the spectrum pretty well down to the very small scale. And now I should say that now we are actually getting models that you can run them for a long time and they don't blow up. For example, one model that has got a lot of attention is this model from Allen Institute and NVIDIA. It uses this spherical Fourier neural operator. It's trained on climate model data at low resolution. There's a preprint you can read. They have actually started adding those boundary conditions that I mentioned. And they get simulations that in some metrics actually look pretty good. You see the seasonal cycle. When you look at some of the tropical waves, they're actually very impressive. But then if you zoom in, there are things like some variables that the models have some unphysical variability. I should say that this model still has a spectral bias, but then I think having boundary conditions and going to lower resolution helps with stabilizing the model. The point is that models that are stable and even like to some degree physically consistent at very long scales, like 100 years, are emerging, which is really exciting and shows the promises of this approach. Okay, so now a little bit about like challenges, and I think to Kartik's question about, I think questions to think about what we should do, the niche questions to identify. I think one big question is this question of extreme events that we haven't seen in the model, right? Even in a stationary climate, there are events that are rare. So we started thinking about these gray swans. One event that happened when we were doing this work was this flooding in Dubai. And if you remember, it was in the media that the amount of rainfall they got was unprecedented for that region. If you just look at the PDF of precipitation over Dubai, this is where this event was. This is the PDF that we had in the training set of the model. So you see that the next event is like almost half of the amplitude. Now, interestingly, we look at a couple of the AI models that have precipitation, and they do amazingly well in forecasting this rain. So this is just one plot, like 8 days ahead forecast. The black line is the observation. The blue line is this like graph gas, which again is very impressive because the highest amount of rain in this region that this model had ever seen is this dashed line. So it's really extrapolating at the tips. So we started thinking about, well, how is that possible? And we basically took a look at the PDF, not just over Dubai, but more globally in the training set, but for the events that had similar dynamics. And we realized that among those, this event actually wasn't that special. So there have been events with even like more precipitation that has similar dynamics. And so the model has seen them in the training set. So currently, our speculation is that the model can actually learn from other regions, which is sort of interesting because latitude, longitude, topography are encoded in the input, yet the model realizes that they can learn from somewhere else, which is promising. So sort of to better understand these like abilities of these models to get the extreme events, we started doing more work. And so we have been training ForecastNet from scratch, from random initial conditions, then we actually manipulate the training set. So we have done work when we remove category 3, 4, 5 hurricanes from the training set. And there we see that the model that could predict category 5 hurricanes well, so if you train the model with full data and look at these are like over 5,000 initial conditions that we have perturbed the model, we have perturbed the initial conditions. You see that ForecastNet does a pretty good job in getting these category 5 hurricanes pretty well. So the y-axis is the pressure drop. So this is like a category 5 hurricane at the end. But when we remove category 3, 4, 5 hurricanes from the model, you see that the model cannot predict these. So the dashed line, this was the smallest pressure drop that the model, the largest pressure drop that the model had seen before. So you see that the model doesn't work well. Just to make sure that this is not because we have removed like a percentage of the data, we have also randomly removed the same amount of data. And then again, you see the model has the same performance. So this is that now, if you have global gray swans, if nowhere in the world the model has seen like these kind of hurricanes, the model cannot predict them. We have now done work that we remove hurricanes only from one region, like we remove category 3, 4, 5 from the Pacific, but we leave them in the Atlantic, and the model can do that translation and learn from one region to the other. The model also do some interesting stuff. I'm not going through the details, but these kind of low pressures, you have seen them in the extratropics, but with a different dynamics. And the model realizes it cannot use that. So to sort of summarize, the models actually do some stuff that are smart, like maybe better than what we expected. Like they can learn from dynamically similar events in other regions. But at the end of the day, if they have never seen anything like this anywhere in the world, they cannot get to these small events, which I think has a major implication for this idea that even if you do 500,000 years of integration, is there any chance that you actually get extreme events beyond what was seen in the 50 years of integrations? So I think here, this is one area where we really have to think about maybe including some physics or coming up with some mathematical frameworks to do this. So one idea that we are pursuing here is to combining rare event sampling methods with the AI emulators. Because of time, I'm not going to talk about it too much, but there are these rare event sampling methods that would allow you to basically inflate the number of extreme events in a simulation. And they actually have been very successful in climate science just by relying on a small number of ensembles you can afford with a numerical model. This is a very nice paper in PNAS from Freddy Boucher a few years ago. You see that even though he only had 1,000 years of data, with this method, he can now actually get pretty good, with reduced uncertainty, events with return period of even hundreds of thousands of years. And here they relied on like a numerical simulation to generate ensembles. So now we are going to use the AI models that they can generate many more ensembles. And we have a postdoc who actually is an AI and science fellow at UChicago, and he's currently pursuing this with Dorian Abbott and Jonathan Ware. Another point I wanted to make was the importance of thinking about the different sources of error, like whether you have approximation error or generalization error, things like rare event, data imbalance, or whether you have a spectral bias as the source of your error, because this is an optimization problem. So I think thinking along the lines of what is the source of error, I think can help with solving the problem. Now, foundation model. So of course, all of this says that, well, we can have weather models, we can have S2S models, we can even get to climate models. So we should think about building foundation models. So there are a number of major questions here, and I think these are areas to really discuss. And they benefit a lot from the work that Karthik and his colleagues are doing in generally foundation models for science. Like the first question is, what should be the design of a climate weather foundation model? There are now a couple of papers, sort of perspective papers, discussing some ideas. One of the nicest ones I really like from Henrik Hamann and his colleagues is the IBM NASA basically roadmap, and they actually do a great job in describing what's the state of the art and some of the questions and challenges. One thing they argue is that we actually should build separate foundation models for different kind of time scales, because otherwise it can be very complicated. Now there's the other question of what is the data, whether we want to just rely on observation data or reanalysis data or physics-based data, or how to combine them. I think one major question is, what are the right algorithms? So of course, self-supervised learning is a major component of a foundation model, and the question is, what are the right SSS algorithms for our kind of data and problems? I think there are actually only a few papers that they do anything like blurring, cropping, but still they use the same kind of SSL algorithm that's used for images and other kind of problems. And I think another thing that's important is to understand what's learned during this, like the transfer learning components. And we had a paper basically that published a year ago. We looked at transfer learning just from one turbulent flow to another turbulent flow, and we did a Fourier analysis of the CNN, and we actually found some interesting results about how the kernels would change, and they actually turned out to be high pass, low pass Gabor filters, and we could connect the changes during transfer learning in the kernels to how the physics of the systems are different. So I think more work along the line of understanding, as we use a foundation model and do the transfer learning, what's learned. I think these can be something I think interesting and helpful, like looking at the homogenization and things like that from a different perspective. Now, so far, I only talked about climate foundation models for climate physics. But of course, as I mentioned earlier, a major component of climate research is actually the human component, the socioeconomic component. So one idea that's emerging is actually to build this kind of framework that you have a foundation climate model and a foundation, basically an LLM. that knows about the policy and socioeconomic impact. And you basically couple them, go from observational data all the way to what the users want. And this is like, for example, one perspective paper from a group in Europe that's leading the Destination Earth project. So I think there are a lot of interesting things to do here at the AI, both for climate physics and connection with social sciences. One last thing to mention, so sort of pursuing these directions, I use Chicago. From August 1st, we are starting a AI for Climate initiative, ACE, that's under the Data Science Institute. So same basically funding that Becca Willett has for the AI in Science initiative. And really we're trying to combine these three directions of climate physics prediction, socioeconomic impacts, climate mitigation, adaptation, all basically empowered by AI. And we have basically a very multidisciplinary initiative. If you look at the leadership team, we have people from, at the Econ Department, Public Policy. Ian Foster is a co-PI. I think he spoke here. And we have an advisory board that comes from all sorts of different departments. Rika Stevens from Argonne, and Michael Kremer, who's an economist, has a Nobel Prize. And he's now very interested in AI, weather forecasting, Bob Rosner, and then Becca Willett and a number of other people. So at ACE, we are very interested in not just connecting people at Chicago and Argonne, but also certainly collaborate with Michigan and with other places along really bringing AI into these directions. And building foundation models is certainly a major component of that. So with that, I stop here and I look forward to more discussions.
Thank you very much.
I had a question about when you talked about transfer learning.
Sure.
I guess I'm just trying to still understand a lot of these things, but I'm just curious. So like, I recall you guys talked about this interpolation techniques. Does that get considered like, if you're talking about a sub-region and you say, okay, our accuracy there is like really good if we want to simulate or model like a hurricane or tornado, but then, maybe in another region, like in a different continent or something, you've got a totally different, I don't know, set of parameters you have to consider, like, that geographical information, right? Geological information. Is the interpolation thought process, is that kind of considered in this too, or with the transfer learning? Like, how can you explain that?
I think that's a great point, and I think that's actually one of the main directions we are pursuing with the group in the econ department. Because I mean, one thing that's nice about these AI models is that doing the transfer learning, even of the most complicated ones like GraphCast, is still very cheap. And so back to your point, of course, the model is currently basically uses a global, loss function, right? There's some weighting with latitude, but certainly not dynamics, right? So as you can imagine, we can have a model that works well overall globally, maybe for some regions better than the other. Now, the idea is if you want to help farmers, right, over India to get the most interested in temperature 3 weeks ahead, now go and do a transfer learning with a loss function that's focused on this variable, this region. And even maybe more than that, bring in some of the observational in situ observations that we have, because Era 5, globally, it's okay for larger scales, but we know that, for example, precipitation or some of the near surface temperatures are actually not the best. So certainly for societal impact, for socioeconomic questions, especially about like farmers, things like that, exactly these, like a transfer learning, more focused on the variable, the region, I think that would be an essential part of it, which actually is going to be not that expensive. So it's more like a domain knowledge question that for what I need to further tune the model.
I had another question, and this was about when you started talking on the errors. You had a slide, if you could possibly go back to it. Still going. Yes, this one. I was very curious, because you talked about, oh, there's this error scaling, and that, we don't know if it's actually like a truncation or approximation error or whatever. So I was just curious for this, is it always consistently this scale? Like, is it always consistently this range that, you would expect this error to pop up this way?
Okay, so if I understand the question correctly, so I should say that this error is always the optimization error. It's a spectral bias. Now, if you're asking why this happens at the wave number 20, I think that's something we are still trying to understand. So of course, I think to some degree, it depends on the slope of the flow. And also, I think this exact number would depend on the size of the network and the data and things like that. So these are some of the sensitivity analysis we are doing. Even if you go to Kramator-Savichinsky, you see this exact behavior. In fact, in that review paper I showed, even you try to learn a delta function, you will see the exact behavior. But I think it remains a question of like exactly like at what scale you start to get this error. I think it depends on the number of epochs you do and a bunch of things.
So then, sorry, I don't mean to cut you off, because I just want to, I guess, further add on to this. If you had all this information of your model, the parameters, all these sorts of things already in hand, and then you run through your simulation or something, and then you're like, can you quantify this error consistently? Like, do you always know, given the prior information, that you would expect to see this error to be at this range?
Maybe we haven't done that. We haven't done a haven't like sweep the like a parameter space. Probably you have to like pick a simple system so that you can do all of these. I agree. I think it would be very interesting. It would be empirical, right? But I think it can be useful. I should say that some of these papers I cited by John Zhu, and this is from Yashua Bengio's group. They actually do a very nice job doing a Fourier analysis of the neural net, usually 2 layers, but really show where a spectral bias comes from. Like, for example, they have expressions like this. It's like this is how the loss would change with the weights, different epochs. This term comes from the Fourier transform of the tangent hyperbolic activation, things like that. So I think like maybe doing something more rigorous would be more interesting, and then confirm that with the kind of analysis that you are suggesting. I think that could be very interesting.
I guess, one of the reasons why I'm very particular in this question is because, right, I come from like some background in reinforcement learning, and I'm just curious, like, if you defined a reward function that is based off of this error, because you know that it's consistent enough, you can trust it given the way you set up your model, how you train it and such, your data, like you already know all this information, right? I mean, I'm just wondering if an RL algorithm could be able to correct that error and minimize it or assist it in some way.
Absolutely. So I'm not sure whether you are talking about doing that during training or during inference, but in fact, during inference, so there's a third component to our algorithm, because if you want to do really long integrations, even though you are doing the regularization, doing Rangakuta, you will still get the spectrum curling up. So we have something that's basically SSL layer during inference, which we don't like. But I think better would be if you can do this during training, but that would require doing basically multi-time step integration during training, which could be expensive, but could be doable. But yeah, I totally agree. Yeah.
Thank you very much. There's some question in the room.
Hey, Pedram, it's Arvind. So I got a more basic question on, so all these weather models, I'm talking only about weather now, they're trained on the simulation data sets. And now we talk about nowcasting. I'm assuming you're going to have for a much higher resolution or a very local area. So what are the challenges when it comes to nowcasting and going from these data sets? The model has learned on these large weather models that have coarser grids than what you need, and closer resolutions, temporal resolution than what you need for nowcasting. That requires, I guess, some sort of, it's almost like a subgrid for my understanding. And that requires us to logically extrapolate in some physics regime. So I'm just wondering, what are the challenges in nowcasting as compared to classical weather forecasting? And I'm just looking for problems where there are gaps where we can address. So,
yeah, no, that's a great point. So actually, there are a couple of papers now about nowcasting. There's also a DeepMind paper. The algorithm is different. Nowcasting is very short time, as you mentioned, a small scale. And they basically leverage observations. So I think that's the direction that many are going. two, even the European Center has a paper that they put on arXiv yesterday that the global forecast is done just directly using observations. I haven't looked at it to see whether the accuracy is comparable to Arrow 5 or not, but probably if you compare directly with observations, it has better accuracy. So I'm not answering your question probably very well, but I think a lot of people are going in the direction of directly using observations, which we have for some regions. And also for smaller regions, you can do high resolution simulations. Like over North America, we actually have even like a smaller scale, high resolution simulations that have been done. But yes, certainly data and how to use different data sets together, I think that would be a major component of designing foundation models for these kind of problems.
Yeah, the reason I asked that is that, we're interested in multimodal type models that take existing simulation data and you have highly local observational data from sensors and whatnot, right? So it requires some sort of a simulation and not even including the physics constraints or anything yet, but that is why I was asking for nowcasting problems based on the topography and terrain is a very significant factor in some of these problems, which has to be explicitly modeled, right? Especially if you have, I'm going to something specific like fire. Wildfire and weather processes being used by large-scale wildfire fires. Now, it is not only an extreme event for that region, and now it's also inducing a fire weather, which has other impacts, and you have pollutant transfer. It's a very coupled problem that is highly local in scale, but from the perspective of that region, it is kind of a really extreme event. So I was wondering if you had any thoughts on where the community going in this direction, or is there a lot of work to be done in this? I'm just trying to pick your brains on what we should do that is useful in some sense.
Yeah, I think my answer would be there's a lot of work to be done. Because again, I mean, this whole area of doing this kind of forecasting is something that even until a year and a half ago, people really didn't think would work this well so quickly. So we are at the point that I think we are thinking about what are actually the most impactful problems to work on, right, and what's needed to address them. So I mean, if this paper, actually, if you see like wildfires and no casting, things like that are part of what they talked about. Again, there is a no casting paper, and it might be just for precipitation that's published in Nature from DeepMind. But certainly that's an area a lot of people are very interested in. And I think part of what's needed in terms of data is like better observational data, like the LiDAR data, radar data, things like that, but also just doing regional high resolution simulations with models like WRF can be very useful. I think there are people who are doing that for California when wildfire is like a major question. But yeah, I think really like thinking about the design of these models and just look at the data you want to use in what sense, I think that itself is something very unsettled in the climate community.
Thanks, that answers my question. Because most nowcasting papers I've seen have been on precipitation and not on the coupled dynamics that happen from these set events. Because yeah, we are also working on a model that has community feedback. Essentially what happens to disaster response also depends on subsequent nowcasting. That's really what I'm interested in. So the couple physics or the couple aspects are not addressed because very early days. So that's what I'm wondering, but this answers the question.
Yeah.
Thank you.
Thank you. Any other questions? All right. Yeah, in that case, so Pedram, I mean, this was really fantastic. This should have been like almost the first talk on the first day.
Keynote.
Yeah, like a keynote style talk to almost set up and place the other talks in the right perspective. So that is one thing. The other thing is I will reach out to you privately. And now we are planning for the next conference in May or June 2025. And we want, obviously, I agree with you that this is one of the biggest successes of SciML. So we want to make sure we get the right people, of course, including you and others. But we also can't get everybody in this domain because we're covering kind of all domains. So I'll reach out to you and, we'll talk more. And independently of that, Alvin and I will reach out to you about some other collaborative work possibilities as well.
Yeah, I think would be great. And again, It's unfortunate that I couldn't be there in person because I'm sure like there could be a lot of interesting discussions. But yeah, certainly we can continue this offline. And if anybody has any question, please feel free to send me emails. And yeah, it would be great to chat more about this.
Yeah. Thank you very much. Again, fantastic talk.
Right.
Again, thank you.
Thank you very much. Thanks, everyone. Thanks, Patrick.